Hey y'all, you survived your first test. Maybe you didn't survive as well as you'd liked, but I think you'll heal. Okay, I'm going to read this out loud. I want to make it very clear that I am reading this out loud, not because I assume you cannot read, but because I need to figure out which ends up. And the only way I seem to be able to do that is by reading out loud. Okay, so we're starting into derivatives. Yay! Finally, calculus. So, rates of change play a role whenever we study the relationship between two changing quantities. A familiar example is velocity, which is the rate of change of position with respect to time. If an object is traveling in a straight line, the average velocity over a given time interval from t1 to t2 is defined as the change in position over the change in time. P.S. that delta S, delta t, that means change. So when I say delta S, delta t, I'm referring to this little Greek letter delta. Some of you may not know your Greek letters because you haven't gone to college yet. So basically all this is right here, is y sub 1 minus y sub 2 over x sub 1 minus x sub 2. So that's algebra slope. And this seems to be a huge hurdle in calculus because our brains are so wrapped up in calculus that we forget our algebra 1. So be aware of that. Remember that. Remember that average velocity or average is simply your algebra slope. So, moving along. For example, if a car travels 200 miles in 4 hours, then its average velocity during this 4-hour period is 50 miles an hour. At any given moment, the car may be going faster or slower than the average. We cannot define instantaneous velocity as a ratio because we would have to divide by the length of the time interval, which is 0. However, we can estimate the instantaneous velocity by computing the average velocity over successively smaller and smaller intervals, and then determine the limit of the average velocity as the lengths of the time intervals get closer and closer to 0. So, if we look at the graph of the position of the object, a secant line can be drawn between the points t1 and s of t1 and t2, s of t2. To clarify here, that T1, I keep referring to it as T1. You might have a professor that might basically chop your head off and eat it for lunch if you don't say it correctly. It is actually said T sub 1. It's because I've taught high school forever and I've gotten used to people just calling it T1, and I should not. In any case, so we are looking at the secant line, and the secant line is the line that I have drawn in here that from your perspective magically appeared. That secant line is drawn through the points t sub 1, s of t sub 1, and t sub 2, s of t sub 2, and the average velocity would be the slope of the secant line through those 2 points. If we move the secant line so that t sub 1 and t sub 2 are closer, then the secant line gets closer and closer to becoming the tangent line. So I'm going to do a little illustration right now. So this lighter line, using a new value for t sub 1, actually brings us closer to approximating the tangent line, and the tangent line would actually only go through t sub 2. Now, it's t sub 1 that is moving closer and closer to t sub 2. Oh gosh, that wasn't a very good arrow. Just pretend that was an arrow. That's terrible. We're bringing t sub 1 closer and closer to t sub 2 to bring that line, which was kind of medium dark and then light and then very dark, coming closer and closer to that tangent line. Each of those lines get closer and closer to an approximation of that tangent line. Okay, so in order to illustrate that, we're actually starting right here. The tangent line is the instantaneous velocity of the object when the time is t sub 1. Velocity is only one of many examples of a rate of change. Our same reasoning applies to any quantity y that depends on a variable x. The average rate of change of y with respect to x over the interval x sub 1 to x sub 2 is the ratio. And again, we have algebra slope. Y sub 1 minus y, or y sub 2 minus y sub 1 over x sub 2 minus x sub 1. In general, this delta means the change in y over the change in x. This is pretty standard notation in mathematics. So the instantaneous rate of change at x equals x sub 1 is the limit of the average rates of change as x sub 2 gets closer and closer to x sub 1. We must consider values of x sub 2 on both the left side of x sub 1 and on the right side of x sub 1 as we take the limit. Let me backtrack just a second. I'm sorry. We were moving t sub 1 closer and closer to t sub 2 over here. Oh, I did it backwards. So it should have been t sub 2 getting closer and closer to t sub 1. I'm sorry about that. Okay, so the instantaneous... So we have to take our limits on the left and our limits on the right. And our algebra slope is now called the difference quotient. The instantaneous rate of change of a function is called its derivative and is defined as follows. So the definition of a derivative is the limit of the difference quotients of, or f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. And you're making that h so tiny that it's super close to 0. When the limit exists, we say that it is differentiable at x equals c. An equivalent definition of the derivative is called the alternative form of the definition of the derivative. And here we're just looking at f prime of c, where the limit as x approaches c of f of x minus f of c is divided by x minus c. And that is a lot closer to algebra slope. That looks a lot more like algebra slope than what the other one does look like. So we're going to look at our first example. A diver jumps from a diving board that is 32 feet above the water. The position of the diver from the water is given by s of t equals negative 16t squared plus 16t plus 32, where t is measured in seconds. Graph this function on your graphing calculator and sketch the result below. And we are only concerned with the diver as he leaves the diving board and goes down to the water. In some problems, we might want to know what happens to the diver after he goes underwater, but in this problem, I already know what the next page says, and we're not interested in what happens when the diver goes underwater. So here we go. We're going to find the average velocity, or the average rate of change at which the diver is moving for the time interval 1 to 1.5. So when we plug in our numbers and do our math, we see that we have an average velocity of negative 4. Make sure you actually do that math to make sure that my numbers are correct. Now go ahead and fill out this table. In order to fill out this table, there's a little calculator trick you may not be aware of, and I'm going to try to draw it out for you so that you can try it on your own calculator. Okay, I've tried to draw it out for you. You need to go into vars, y vars, and pull up y sub 1. And when you pull that up, you can put in your x values and you will get the appropriate y values. And when you do this, you should get negative 14.4. If you do not understand what I'm saying, we need to talk about that during class tomorrow. Otherwise, I want you to take the next few minutes to fill in the rest of the table. please press pause and fill in the rest of the table, then check your answers. So when you go to finish this table and you look at your values that are closest to t equals 1, both values are super close to negative 16. Now, I want to point out something, and this is really important, and I cannot emphasize enough how important things are when I say they're really important, because I try not to say that too often. There are two things that are really important so far. One, and you learned the hard way that this is true, if I ask about limits, you need to state them as limits. This next thing, you must use approximately. We cannot, given the manner in which this problem is stated, we cannot say that our instantaneous velocity is exactly negative 16. We know that it is approximately negative 16. Some other rules you've learned since school has started: if you're going to write a decimal, make sure you bring it out 3 places beyond the decimal if you're rounding or truncating it, bring it out 3 places beyond the decimal, number 1. Number 2, go out of your way to leave things in fraction form. Fractions are more exact than decimals. Okay, so we found that the instantaneous velocity was negative 16. We found that by coming closer and closer in or finding the limit of that average velocity as it got closer and closer to the x value of 1. Okay, I'm going to make sure I didn't skip a slide. Okay, given x squared minus 4x, sketch the function and the tangent line to the graph at the point where x equals 3. Graph your curve, graph an approximation of that tangent line. There you go. Based on your sketch, do you expect f prime of 3 to be positive or negative? So if you look at that, you can see that your tangent line has a positive slope. So if you did it right, your tangent line is going to be positive. So we are going to compute this derivative by using the definition of the derivative, by using the alternative form of the definition of the derivative, and then by using the shortcut that you learned last year, which I think some of you have not learned, so we will talk about that a little bit. Okay, now I want you to push pause. I should have asked you to push pause before now and work this out on your own, then check your work. Except I made a big boo-boo and I magically appeared a 4 there. Thank you for calling me out on that, Liberty. Okay. Now, we're going to see what cancels. The x squared cancels with the x squared. The negative 4x cancels with the 4x. And in the next step, because we are dealing with a limit, we can cancel an h from each term. And we see that our derivative is 2x minus 4. And now using the alternative form of the definition of the derivative, we go ahead and plug in x and c, and now we're going to factor things. But before we factor, we need to regroup because we are specifically looking for groupings of x minus c. And just as before, things canceled beautifully. An x minus c cancels from each term, and we are left with x plus c minus 4, but x is approaching c, so we actually have 2x minus 4. Now, in years past, people saw this in on-ramps pre-cal. From what I can tell, y'all, since the school year had ended, I'm not really sure what happened, because I know on-ramps covers it. I don't know. Y'all need to explain to me what happened and why you don't remember this, or some of you just maybe spaced at the beginning. Okay, so now we're going to talk about the shortcut. We're going to talk about the shortcut as quickly as we can. We've got the original function is x squared minus 4x. Oops, that's sloppy and I can't see what I'm doing. F of x equals x squared minus 4x. And we take down our power and subtract 1 from the power to find our derivative. Take 1 down from the power and subtract 1 from the power, and we get 4. Now that little prime means that it's the derivative. Boo, boo, boo. So, for further clarification, your power here was 2. Take it down up front, subtract 1 from 2, we get 1. Our power here was 1. Put it out front. 4 times 1 is 4. Subtract 1 from that power. 1 from 1 is 0. So our variable goes away. Next up, we're going to talk about differentiability and continuity. A function is differentiable at x equals c if the derivative of f exists at x equals c. In order for the derivative to exist at x equals c, the graph must have local linearity there. In other words, if you zoom in way in at x equals c, the graph will look like a line, but not a vertical line. A function is not differentiable at x equals c if f has a sharp turn at x equals c, if f has a discontinuity at x equals c, if f has a vertical tangent at x equals c, or if f has what is called a cusp at x equals c. Okay. Here, it is not differentiable. Number 1 at the sharp turn, it's not differentiable because there's a sharp turn. Number 2, there's a discontinuity. Number 3, there's a vertical tangent. And number 4, there is a cusp. Okay, covered it all. Here we go, onwards and upwards. List the x values for which the function appears to be discontinuous and not differentiable. Go ahead and do that. Pause your video and try to figure that out on your own first. Okay, so you should have been able to find the points of discontinuity fairly easily. You may have forgot to include the endpoints. Try to remember those little endpoints. They seem unimportant, but there are no arrows there, so that means that it doesn't keep going. And remember that when it's not differentiable, you also need to talk about the points of discontinuity in addition to any points where there might be a cusp, a corner, or, oh, y'all, I forgot one. I'm being sassy to myself, not you. X equals 4. There's a vertical, I didn't draw that very well, but somewhere in there, there is in fact a vertical tangent. Oh gosh darn it, it's time for class to start. Okay, I'm gonna flip the page and come back to y'all in a few minutes. Now we look at our next graph and we decide where our slope is 0. So that would be at places like E or B. And positive would be C and D, and negative would be A and F. I went through that a little too fast. Hopefully I will have an opportunity to go over that in class. Okay, so now we're going to look at a function that satisfies f of 2 plus h minus f of 2 equals this gibberish, and we're going to find f prime of 2. This tends to be the kind of question that shows up on the AP exam and on tests. So I'm going to try to talk about that very slowly. We are going to replace x in this equation here with 2 because we're looking for f prime of 2. Okay, so all I did was replace x with 2. Now I have this weird piece of information up here, and I'm going to replace this whole expression with that. So I'm going to go ahead and write, instead of the stuff in the numerator, I'm going to write that 5h minus 3h squared plus 9h cubed. And sometimes they ask strange questions like this. We still don't know what f of x really is, but we're still going to be able to find an expression for f prime of 2. We see here that one of our h's can cancel because it is within a limit, and we will get an expression for f prime of 2. And we see that it's 5 minus 3h plus 9h squared. Okay, I will try really hard to give you many examples of this sort of problem, because this sort of problem is super common and it tends to throw people off their game all the time, because this random what is going on there, they've redefined the whole game, right? Okay, make sure you're taking notes and pressing pause and all that jazz, because you're going to be lost if you don't. Next up, we are going to find the limit as h approaches 0 of f of h divided by h. Oh, no, we're not. We're going to find the definition of the... What? Things got cut off. I need to find... Oh, there. Oh, gosh, look at that. Look at that. What? Things converting to PDF. There. Find f prime of x. So we're going to work on that real quick. So we write down our definition of our derivative, and then we remember that y, oh gosh, is just a variable, and h is just a variable. So now we're going to just take this definition up here and use it here, but instead of y, we're going to use h. Y'all, but I made a rookie boo-boo. Just like you. I forgot the limit as h approaches 0. And the limit as h approaches 0. Oh my gosh, was I recording that whole time? I hope not. Okay, so now we see that, let me see how I want to talk about this. I'm actually going to break it up into 3 bits. It's going to be easier for me to talk about if I do that. Okay. So now we can use this information that f of h over h, the limit as h approaches 0 of f of h over h equals 2. So we can actually make this bit, boy, that's a terrible 4, isn't it? Be negative 4 times 2. And on the next bit, our h's cancel. So we're left with plus 9x. Now we need to think carefully about the first expression. Okay, so we don't know much about f of x. And because we know very little about f of x as h approaches 0, we need to assume that it's infinity. If that limit was in fact 0, which it may be, things will be clearer on a test, by the way. The whole entire derivative would have been 9x minus 8, but because f of x is undefined, then we need to stick with this infinity answer, or the limit does not exist, in the words of Lindsay Lohan. And if you don't know that, you need to go get yourself some education. Okay, flipping the page. Given that the limit as x approaches 5 of f of x minus f of 5 divided by x minus 3 is 3, which of the following must be true, might be true, or can never be true? Remember that the alternative form of the definition of the derivative is f prime of c equals the limit as x approaches c of f of x minus f of c all over x minus c. So f prime of 3, or the derivative, is 3, and that must be true because by definition that's what we've got at the top there. So this one must be true. The second one, that derivative can never be true because we've already decided it's 3, and 3 does not equal 0. We have no idea what the value of f at 5 is, so that might be true. We have no way of knowing. And must it be continuous at x equals 0? We're talking about the derivative at 5, so we don't know that much about what's happening at 0, so that might be true. And finally, f is continuous at x equals 5. In order for something to be differentiable, it must be continuous at that point. Okay. Let me double check. I think I am done. Yay!